welcome back. It's Friday afternoon. Perfect time to start a whole new project. Yeah, everyone's focused. You're at peak energy. Nothing can distract you from the engineering tasks at hand. Right? Definitely, that's the case. So one thing about the website, when we switched from Google to Microsoft, I lost a whole bunch of videos and notes and stuff. So the quick fix was I just deleted all the references to anything that had a Google link. So they're not there, so you can't click on them and say, hey, this one doesn't work. It's just, it doesn't exist. So now it's gone. Not my ideal fix, but it did fix the problem of broken links because now the link doesn't exist. So hopefully that helps, clears up some confusion. Now there are, if a link is there, it should still work. I might have missed some. Okay. But today, oh wait, I wanted to come back here. I wanted to take a look at our first case problem. So this will be a group project. There's no real cheating on it. It's just stuff we're talking about it and kind of working through it together. The idea is this is a real kind of engineering approach. There's there could be lots of unknowns and things that aren't really accounted for. So do you want to account for them or do you want to ignore them? Either way, it's a decision on your part. But we have 3 different ideas for stopping something that's falling. One is a spring, one is some kind of fluid, and then another one is some kind of rough walls, using friction somehow. So that's what we're working with, is we're trying to figure out either which one of these is best or something. End goal would be present some create some graphs that show either it works, or if you want to say none of them work, you're all ridiculous, get your hands off the wheel, then you can make that message. You don't make a lot of friends that way, but you can do that. It's just now you have to do everything yourself, which gets very tiring as an engineer. So this is what we're working with. You have a few different options. Can you show either they work or that they need work? So let's take 30 seconds, just kind of think about what these are, and just what are the initial gut reactions? What do we think is going to happen? What do we think we need to do? Any kind of thoughts that way. This is just the brainstorming phase. All ideas. Get them all out here. Some brainstorming. What do we think? Okay, I like the idea of are you thinking actual force times time?
Yeah, because this
So for a crowd that says they're not on it, that felt like out of it, some great questions came up. So where do I start? One of the ones was, even if you have a frictional wall, even if there is friction between an object and a wall, if there's no normal force, there's no friction. So where's the friction coming from? How is it stopping? So there's different ways that we could kind of say that. We could say there's a constant, like, normal force from the wall, right? Like, similar to how brakes work. Just you put the things into contact, now you have friction. The more you press on it, the more friction you have. One way we think about it. One idea was, like, if the walls are sloping, like, it keeps getting narrower, so you keep increasing that contact resistance. Another thing that came up was, like, how in block B, how buoyant is that thing? Is this a beach ball falling into a pool, or is this a rock falling into, like, a lake or something? Also a good question. My initial kind of, at least, like, my initial engineering intuition is, like, the fluid is going to be a lot less dense than whatever I'm trying to stop. That's what I would initially think. It's like, if I have something that's 0.1 kilograms, I don't want 10 pounds of fluid to try to bring it to a stop. I would want something, like, just a little bit, just enough to, like, something light, something that'll slow it down. So roughly, I would say, and that's up to you, whether you want to think, like, buoyancy is an extra stopping force, or you just want to say buoyancy is out altogether. Other things that came up? Oh, and then the other part was, what graphs do we need? Which I followed up with an annoying question of, well, what graphs are important? Because that's what I'm here for, is just asking stupid questions. When you get to be, like, as educated, like, your peak of education, you learn, like, oh, I should have been asking all the dumb questions this whole time. Like, after you get, like, all your degrees, like, I missed out on so many dumb questions I could have been asking. Like, there was so much I could have learned. So now I get to come back and do it to you. Yay. So what graphs would be important? Position, okay. We can have position over time. Usually that's, like, when someone says, solve this differential equation, they mean, like, show me the position, like, what happens. So position would be great, yep.
Position, velocity, acceleration.
We could have position, velocity, and acceleration, all one graph. Like, position as a function of velocity and acceleration, like in a three-dimensional hyperspace. Three separate graphs. We could have them all versus time, right? There's a cool type of graph called a phase plot, where you plot velocity as a function of position. And that one might be useful here because it would show us at what position we hit zero velocity. That might be kind of nice. Phase plots are good. And then someone else brought up maybe a free body diagram, which is not, it wasn't what I was thinking of when I asked for graphs. But yes, free body diagrams, that is the key to dynamics. It is, like, the most crucial element is a free body diagram. Then there's an extra bonus diagram. You've unlocked this new diagram. The kinetic diagram is the next one that we have to deal with. So once we have the two of those, we can do all sorts of cool stuff. This is just the brainstorming phase, like questions, initial reactions, anything like that. What else did you talk about? Or that captured the swirl of ideas? Totally captured this moment in time. Yeah.
Another thing we said is, like, when does the clock stop? For instance, the spring one.
Yeah.
Does it start accelerating again, or is it going to stop when it
Okay.
zero?
Yeah. So, and this is this is a great question about like which one of them will even stop this object. And so with the spring, you're right, that if you drop something onto a spring and the only thing you consider in your model is that the spring compresses and applies a force, it doesn't stop applying force because the thing came to a stop. Now you have maximum compression and it's going to bounce back. So if that's our model, then that's the model, right? It will bring it to a stop, but it's going to launch it right back out. Yeah, great idea. Great, like, observation. So now, I don't want to give, I know how I would approach it, but I want to know, like, just based on how you're coming into this class, what you've read, or kind of, like, if you've done some AI, like some of the learning coach readings and stuff, how would you approach this problem? Like, what's your very first step? We're not going to solve it all in one go, but what's the first thing that you want to do? And I don't want to give any direction. I'll tell you how, like, I would approach it based on what people are doing, but I just want to know what's your thought process here, because it also talks about, it also reveals, like, what did you assume with where you started. Like when I was a student, I would jump straight into equations, like just dump it into a kinematic equation. But there, by using a kinematic equation, I had already assumed, like, okay, it's got to be constant acceleration, and it's got to be a point mass, and it's got, like, there's all these other things that were assumed along the way. So that's what I want to know. Where are you starting with? What do you want? What are you aiming for first? What do you think? And again, group projects, the goal is talk to each other, like, just kind of work it out. What do you think? What's your first step?
Draw a free body diagram along the problem with the boxes. So that basically drawing is gravity down, put a spring.
Okay.
Assume that like it's gonna be a free fall. Spring.
Yep.
And then as when the graph stops, you know that like there's like ideal, you know, it's going back up.
right, so questions that came up were kind of like, we're like two parts of like when we're turning in this group project, like how are we supposed to work with the group members? This is not the only time we're gonna come back and keep working on this on Monday, probably Tuesday. Or sorry, not Tuesday. Yeah, you have to be here every day next week to get this done. No, Monday, just the class time. We're gonna meet in the class, keep working on this problem, and kind of we'll talk through the physics and engineering of these things together. And then like what is expected, like what is A-level work. Main thing is like try it, like do something. We already talked about like free body diagrams. So at least, like if I was going to present like my A-level work for this, I would have like a free body diagram, I would have all the differential equations listed out, I would list out every assumption I made, and then my graphs would like support the conclusions of like, this is the best stopping mechanism because look at this graph and how much graphiness it has, that it stopped here, and this was where velocity is 0, this is the position that it landed on, this is whatever my reasoning happened to be. So yeah, answering kind of those logistic questions. But getting back to some ideas of where to start. So some people started off, and I kind of like this approach of, in these 3 cases, since we're asked for a graph, just a hypothesis graph, like something, what do I expect to happen? So I saw some kind of like, in here, this thing's gonna start up there and maybe like oscillate, because there's a spring. We didn't say there's like friction or damping or anything, so just, you know, it's gonna bounce up and down, something's gonna happen. What did you think for like falling into this fluid for like a hypothesis? Did anyone else try a hypothesis graph of just like roughly what's gonna happen? What happens if we drop something in a fluid? No one's ever like dropped their phone in a pool and like,
There'd probably be like a constant deceleration.
oh, constant deceleration. So you think like, so if we had V versus T, do we think it's constant like this? Yeah?
The velocity would be constant.
Oh, constant. Yeah, so if we had V, it would have a constant slope. Is that right?
It would be like 2 curve.
For velocity? Oh, so velocity curving. What do we think? Curving down or curving? What is that? Happy face or sad face curve? Top or bottom? Or like going down or going up? What do we think?
If the block's the same width as that width, wouldn't it not go up?
If it's the same width?
Yeah, wouldn't it not go in?
Oh, if it's totally
The water-
incompressible, right?
Water wouldn't be able to come out to the sides.
Okay, yeah. Maybe, yeah. Yep. So kind of like, oh wait, the concave up, wait. Yeah, up, this one, right? Concave up, like that? It's catching up. That one? Yeah. Okay, all right. So initially a lot of velocity loss, and then over time slower velocity loss. Maybe something like this. What about the last one, like friction? If there's even friction here, no normal force. Paranormal forces, that's how we get it. I went to grad school at Columbia and they filmed Ghostbusters at Columbia. So I actually when I was going to classes, I'm like, that's where Egon was. I'm like, oh my God, that was Dr. Spangler. And like, look, that's their old building. And other people are like, it's not that big a deal, man. They film movies in New York all the time. I'm like, but not Ghostbusters. This is the coolest. friction. What about friction? What's friction gonna do?
It's gonna be a constant, so kind of like the liquid graph, but it'll be just straight ahead.
Yeah, so if we had V and T, it should be like something. Like friction is not, it doesn't change. Like once you have friction, it just is friction. So something's gonna happen, kind of like that. I like that. So here's our hypothesis graph. Hypotheses. The other thing that someone brought up, probably just because I was like glowing about free body diagrams, was someone's like, I'm gonna start with a free body diagram. I'm like, yes, do that, awesome. So, somebody said it, so now you all have to do it. And I mean, it's part of this class anyway, these free body diagrams. But what do the 3 free body diagrams look like for A, B, C? Block hitting a spring, block hitting a fluid, and a block hitting some kind of frictional surface. What do the free body diagrams look like? Do we all know how or what free body diagram is? Yeah? Okay. So then, do we want to consider it a point mass? We do? Just like, yes, please, point mass. That's fine with me. We don't have to belabor it anymore. Point mass is fine. So we have 3 points, A, B, and C. What are the forces acting on those points? What direction are they pointing? What do they look like? Oh, yeah. Oh. Done?
Well, I didn't do point masses, but
Oh, you didn't?
I'm trying to figure out how I should draw the third one because friction is going to be pointing off.
This one, so far I've seen, heard kind of described all three of them. No matter what we do, they're still, whether it's in a fluid, whether it's bouncing on a spring, gravity still pointing down. Nice, good old dependable gravity, right? And then, what does the force look like for that spring? That one I saw. Is it pushing up or pushing down? Up? Say up, all right? I'll say like FS, force of the spring. What about for this fluid? And this one, yeah, first tell me what the force looks like. Pointing left, right, all over, static, it's like pressure from the fluid. I don't know. What do we think? Yeah, oh, water tension? Ooh, that's a whole nother, surface tension problems. We're gonna, yeah. I mean, we can't, it is cool, like I like surface tension problems, but it's a pretty big object falling into buoyancy. So if we want, we could say there is some kind of buoyancy, or we could say we could put it there and say, well, buoyancy is probably close to zero. It's up to you. It's your engineering. It's your case. You can make the case. I really slowed down on YouTube today. It's catching. All right, so here is, I'm gonna call it like an FV, like a viscosity, or damping. Like a lot of times it's called like FD, like damping. So let's do that. We know what the constant B is, like, so it's something falling into a viscous fluid, so there's no turbulence happening as it's falling into this. It's all viscous. So we can describe that with B. The force is a constant times speed. So the faster you move, the more force is applied. The slower you move, the less force is applied. That's one way to kind of deal. And it kind of takes care of a lot of these questions of like, how big is the opening? How dense is the fluid? What's the viscosity of the fluid? It all gets lumped into one thing called B, and it's just kilogram per second.
Also for like air resistance too.
Air resistance is similar. Like if we talk about drag, for drag, usually we have like coefficient of drag, cross-sectional area, so how much area does the actual air see, the density of the fluid that you're moving through, not the density of the object, and then what speed are you moving, and speed squared. But that one's drag, so usually this only becomes, because it's a squared term, it only becomes important if you're doing like, at least for a person, about 20 miles an hour for a person. If you're smaller, it's probably even lower, like lower cross-sectional area. Depends on how fast, when you want to consider it, but we don't have to worry about drag, at least for now. Unless you want, I mean, you're welcome to. You can worry about whatever you want. All right, friction, I saw a few different things, but some people kind of said like both walls are gonna have a force of friction. But what about like that normal, like friction needs a normal force, right? So where's the normal force coming from? I mean, yeah, we don't need to overthink it, right? Like it's gotta be normal to the wall. Like it's gotta be this way. We can say that it comes from both sides, but there's got to be, if there's friction, there's got to be some kind of normal force creating that friction. And some questions came up of like, this is impossible. Like, how could you possibly assign this? I mean, they weren't like as like theatric as this, but like, how could you possibly assign this problem that's unsolvable? There's not enough information. Welcome to the real world. Like, there's never enough. People give you these design problems. My brother was in the bike industry for a long time. Someone came into his bike shop and they said they wanted an electric bike. And at the time, electric bikes were like still kind of new, like some people had them. He's like, okay, we can help you out. And they said, yes, I want an electric bike, but I want a rechargeable battery. He's like, yep, makes sense. And then they said, I want an electric bike with a rechargeable battery that recharges as I pedal. And then he stopped and he's like, do I need to explain thermodynamics to this person trying to buy a bike? Or is there some other way? Like, you can't, if you're pedaling a bike, let's say it takes 100 watts to pedal the bike, but you also want to recharge your battery with 100 watts. You need to pedal twice as hard for the same amount of speed. But this person is just like, no, but I'm already pedaling. Why can't I just recharge my battery as I pedal? The pedals are moving. Shouldn't that recharge the bike? It's like, you can't have both. You can't have both. Technically, you could do that, but it would be very... This person specifically, like, they clarified, like, definitely, while any pedal stroke should increase battery life. Yeah, they were very... Because regenerative braking, that's a great way to like recover some unused energy. Like, rather than just expel waste heat, put some generators on there, turn it into some electricity. We running out of time? Okay. Free body diagram, if all else fails, always start with free body diagram. It never hurts. Sometimes it's really simple, like this one is about as simple as we can get, but still, now we know we're not considering anything else. It lays out all of our assumptions and all that. So we'll keep working on this, and we'll come back Monday, give it another shot. Thanks.